say you're sorry.
Hello, my name is Muhammad Luman Hakim bin Dahlan.
Hi, my name is Nur Aina Sakinah binti Razali and my student ID number is 2022418958.
I'm Nuliana Jasmine. My student ID is 2022637024.
Hi, my name is Nur Anissa binti Abdullah and my student ID is 2022812628.
What is the static electricity, electric charge, and its conservation? Okay, we go to the first thing is static electricity. The definition of static electricity is a stationary electrical charge that is built up on the surface of material. Static electricity is the result of an imbalance between negative and positive charge in an object. This charge can build up on the surface of an object until they find a way to be released or discharged. So we look at the diagram. The axis positive charge on hair and axis negative charge on balloon. So when the positive charge and negative charge have a contact, so opposite charge they will attract. Okay, now we go to the second point is that the electric charge. What we should know about the electric charge? The first thing is rubbing materials does not create electric charge. Remember that rubbing materials does not create electric charge. Okay, the second point is it just transfer from one material to other. Okay, now we should know that where do charge come from. Okay, the first is if electrons equal to protons, so they will be neutral. No negative charge and no positive charge. They will be neutral. Okay, second, if electrons greater than protons, so they will be negative charge. They will gaining electrons. Okay, and the third is if protons greater than electron, so they will be positive charge. They will losing electron. Now we go to the conservation of charge. Law of conservation of charge is the net amount of electric charge produced in process is zero. Okay, as we can see, as we can look to the picture, when objects come into contact, electrons can move from one object to another, causing one object to become positive charge, is that losing electron, and the other negative charge is that gaining electron. This transfer of charge maintains the overall balance in the system. Similarly, in processes like charging by induction or separation of charge in an electric circuit, the total charge before and after the event remains the same. The conservation of electric charge is a fundamental concept in electromagnetism and plays a crucial role in understanding the behavior of electrical charge particles in various situations.
Now we are going to get into insulators, conductors, and induced charge. So insulators are materials that do not allow electrons to flow through them easily. In Malay we call it penebar haba, which for example are glass, wood, wool, and obviously plastic. the things that when you touch it, you will not get some type of electrical shock when you do so. However, conductors are the opposite of insulators, which is materials that allow electrons to flow through them easily. Electric charges move freely in response to an electric force, such as aluminum, steel, gold, and just iron. And now we're going to induced charge. There are different types of induced charge. For example, one is charging by conduction, which involves direct contact of a charged object to a neutral object. For example, we can see here charge by conduction while it's touching is we have positively charged rod and a neutral metal plate, and when you touch them together, it will attract electron flow so that the positively charged rod will be less positive and the neutral metal will become positive because the electron just flow out. Next induced charge is charging by induction, which involves the charging of one object by another without any direct contact. So if we look for the example, charging by induction conductors, we have a neutral metal sphere with negative charge rod, and we get them close to each other but we did not quite touch them. The positive charge will be attracted to the negative charge rod, while the negative charge that they have in the neutral sphere will just go to the ground, which it will still flow out, but it doesn't flow out to the rod. It will flow out to the atmosphere and drop, which makes the neutral metal sphere just now became positively charged. And the last example for induced charge is charging by friction. For example, for charging by friction is rubbing a balloon against your hair. We do this a lot as kids. The electron from our hair will move to the balloon, which will make the balloon negative charge and our hair became positive charge. That's why when you're done rubbing your hair with the balloon and you take the balloon off and then you get it near your hair again, your hair will stand because it's attracted. The positively charged hair is attracted to the negatively charged balloon.
Coulomb's law. Definition of Coulomb's law is the electric force between two charges is proportional to the product of the charge and inversely proportional to the square of the distance between them. Coulomb's law can also be described as F equal to K Q1 Q2 over R squared. That is, K is Coulomb constant, which is 9.0 multiplied by 10 power of 9 Newton meter square per Coulomb square. Q1 is charge on mass 1, Q2 is charge on mass 2, and R is the distance between the two charges. On this slide, as you can see that the charge are opposite is attractive and the charge that are same is repulsive, which is charge positive and positive is repulsive and charge negative and negative is repulsive too. But for charge positive and negative, it is attractive. Electric field. Electric field exists around charged object. Electric field is a vector quantity and the SI unit for electric field is Newton per coulomb. Electric field also can be described as E equal to F over Q and E equal to KQ over R square. As you can see, these are the electric field around negative and positive charge. When the charge is negative, electric field are into the charge, and when the charge is positive, the electric field are out of the charge. These are the electric field that can be found in daily life, such as lightning, party trick magic balloons, small sparks in blanket at night, and pieces of paper attracted by gold.
Okay, next we go to the field lines. What we should know about the field lines. The first thing is indicate the direction of the field. The field is tangent to the line. The second is the magnitude of the field is proportional to to the density of the lines. And the third is field lines start on positive charge and end on negative charge. The number is proportional to the magnitude of the charge. From the a few diagram above, I want to explain about what we should know about the field lines. I mean the properties of field lines. Okay, I want to explain the diagram. The first is electric field lines always begin on a positive charge and end on a negative charge. So they do not form closed curve. They do not start or stop in mid-space. From the diagram, I can explain that the number of electric field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. The third is the electric field lines can never form closed loops, as the line can never start and end on the same charge. These field lines always flow from higher potential to lower potential.
Now we're gonna get into the calculation of electric field. For example, the question is calculate the magnitude and direction of the electric field at point P, which is 30 centimeters to the right of a point charge Q equals to negative 3 times 10 powered by negative 6 column. So we have our R is 30 cm. We change it to meters and then we're gonna get 0.3 meters for our R. And Q they give us is negative 3 times 10 powered by negative 6 column. And K is actually our electrostatic constant, which is 9 times 10 powered by 9. And for electric field, our formula is E equals to K times Q per R squared, which we will list down is E equals to 9 times 10 powered by 9 times by negative 3 times 10 powered by negative 6, and all of that combined we're gonna divide it by 0.3 squared, and then we're gonna get our E negative 0.3 Newton per column to the left, which is why it's negative.
1.7 Electric flux and Gauss law. Electric flux. Definition for electric flux is how much E penetrates through surface. Maximum when surface perpendicular to field. That means theta equal to 0. Flux equal to 0 when surface is parallel to the field. That means theta equal to 90. SI unit for electric flux is Newton meter square per coulomb. Formula for electric flux is EA cos theta, where E is the magnitude of the electric field, A is the area of the surface, theta is the angle made by the plate, and the axis parallel to the direction of flow of the electric field. This is example question for electric flux. Calculate the electric flux through the rectangle shown. The rectangle is 10 cm by 20 cm. The electric field is uniform at 200 Newton per coulomb and the angle theta is 30. For solution, first we have to know the information that we have. In this question, we have area, electric flux and theta. So we can use formula EA cos theta. But the area in this question is centimeter. As we know, SI unit for area is meter. So we need to change centimeter to meter. And then we can calculate the area. The area that we get is 0.02 meter square. And then we can put the information into the formula. And then we can calculate. So electric flux that we get for this question is 3.46 Newton meter square per coulomb. Gauss law. Definition for Gauss law is the total flux enclosed in a closed surface is proportional to the total flux enclosed by the surface. Or we can use this formula, where Q is total charge within the given surface, E naught theta is the electric constant. Gauss law theorem. You can see the formula. The Gauss law theorem relates the flow of electric field lines flux to the charge within the enclosed surface. If no charges are enclosed by a surface, then the net electric flux remains zero. This means that the number of electric field lines entering the surface equal to field lines leaving the surface. Gauss law to Coulomb's law. As you can see, this diagram show you how you can get Coulomb's law formula from electric flux formula. So we use spherical Gaussian surface. As we know, a formula for electric flux is EdA, where E and dA are parallel everywhere on the surface and E is constant everywhere on the surface. So we can use EdA equal to Q in per E naught. So we get D for spherical Gaussian surface is 4 pi r squared, and we can put 4 pi r squared into this formula. So we can get 4 pi r squared equal to Q in per E naught. 4 equal to Q in per 4 pi E naught r squared. As we know, K equal to 1 per 4 pi E naught. So formula for Coulomb's law that we can get is E equal to K Q in per r square. Conclusion. As you can see this picture show you the mind map for all the topic in this chapter, electric charge and field. In this chapter, you must to know a difference between positive charge and negative charge. Other than that, you must to remember all the formula in this chapter, and you must to know how to calculate the electric flux and electric field. So that's all from me and all my friends. So thank you for watching our video, and I hope you can learn and you can get some knowledge from this chapter. Thank you.